Today we'll explore net forces and friction. Here's our objectives. Look how far we've come in our study of objects in motion. How much can we figure out with just 3 simple measurements? Gerty is driving a 12,000 kilogram school bus. She sees it's traveling at 11 meters per second when she hits the brakes and brings it to a stop in 2.2 seconds. Can we create a free body diagram which describes the bus coming to a stop? In order to do this, we should list what we know and identify what we're solving for. These are the variables we know. To create a free body diagram, we'll need the friction and weight, which are both forces. These equations can help us out. We can solve for the distance the bus traveled while Gerty applied the brakes to stop. Using the initial and final velocity and time, we see it traveled 12 meters while coming to a stop. We can also solve for the acceleration of the bus using the same variables. The acceleration is -5 meters per second squared. How about the net force acting on the bus? Using the acceleration and the mass, we can see the net force is -60,000 newtons, which is equal to the friction created by the brakes. And what is the weight of the bus? With the acceleration due to gravity and the mass, we can calculate the force of gravity. Using a speedometer for speed, a stopwatch for time, and a weigh station for mass, we were able to calculate the distance it took the bus to stop, its acceleration, the force of gravity acting on it, and the amount of friction needed to stop the bus. Pretty impressive. Now we'll create that free body diagram for the bus as it comes to a stop. How many arrows will we need? Since Gerty takes her foot off the gas when she applies the brakes, there are only 3 forces acting on the bus. And they're shown like this. The normal force and gravitational forces are equal and opposite, and friction slows the bus down. What about the force needed to get the bus to start moving again? Does it take more force to get an object to start moving or to keep an object moving at a constant speed? Would Gerty have to push harder on the gas pedal to start the bus or to keep it going? If you guessed it's harder to get the bus to start moving, you're correct. Because you're trying to overcome static friction, friction which acts on a stationary object. This is greater than kinetic friction, which acts on objects that are in motion. What about the amount of friction acting on the bus compared to the amount of friction acting on a car? The bus has much more mass, therefore it has much more friction acting on it. So there are 3 variables we'll have to consider when trying to calculate friction. Is the object moving or at rest? How much mass does the object have? And also, what is the quality of the surface? Because if the bus was sliding on ice, there'd be very little friction. The quality of the surface is described by the coefficient of friction, symbolized by mu, a ratio between the normal force and frictional force. The equation looks like this, and it doesn't have a unit since it's a ratio. Remember the symbol for coefficient of friction can be for objects at rest, mu static, or objects in motion, mu kinetic. Here are some examples. Can you see that steel and ice have much less friction between those surfaces than the friction between rubber and concrete? Why is it important for rubber tires and concrete to have so much friction? Lots of friction ensures that cars don't easily slide off the road. So let's try this again. How much force is needed by Gerty to get the bus to start moving again? We'll need our equations and a free body diagram. The normal force acting on the bus in this case is equal to the weight. And the coefficient of static friction is 1 between the rubber tires and the concrete road. Using this equation, we see the bus needs 117,600 newtons of thrust to overcome the static frictional force. But once it's moving, it won't need so much force. Since the coefficient of kinetic friction is 0.7, it only needs 82,320 newtons to keep the bus moving at a constant speed.